Alright, so my next topic is on standard, cyclic, modules, and characters. Modules and characters. They have it as a backwards 3, but I think that's just going to look like I'm writing the number 3. So let's maybe go the Mr. Saturn route. Go like that. Be the center of the universal algebra of our Lie algebra. This is going to be the set of elements. Yeah, it's the center. You know what the center is. An automorphism sigma of L unto itself extends, we know, uniquely to an automorphism of universal enveloping algebra of L. Noise are happening, so G once again as our inner automorphisms generated by the exponential of the adjoint representation of nilpotent atoms acts on the universal enveloping algebra of L, mapping this thing to itself. Alright, and then we get a lemma right off the bat, which is this is the set of interior automorphism invariants of the universal Lie algebra of L. And the proof? Well, we know first off it commutes with all nilpotent x in L as it commutes with all of x of L. So the bracket. So we know that 0 is equal to the bracket of x on z for z in our funny thing, which is the adjoint of x on z. And we know that the exponential of the adjoint of x on z is going to just give us z. Thus all sigma and g fix our arbitrary z in our fancy set there. Now conversely, let g fix an element x in the universal enveloping algebra of L. We're going to fix a root in our root system and take a non-zero x alpha in its root space. Fn is the adjoint of x alpha. Well, suppose we have t such that the tth power of n is non-zero and the t plus 1 power is 0. So it's the largest non-zero power of our nilpotent n. Now we want to choose distinct scalars called ai from 1 to t plus 1 in f. by our hypothesis. The sum go from j equals 0 to infinity to t of ai to the j over j factorial times n to the j is then going to fix x, the determinant of the matrix. You have 1s, and then a1 through at plus 1. All the way to a1 to the t over t factorial through at plus 1 to the t over t factorial is 1 over the product from I equals 1 to t 1 over I factorial. We'll call it j actually. Keep things a little less ambiguous. Times the Vandermonde determinant, which is the product for I greater than j of our ai minus aj, which is non-zero. Thus, we can find scalars bi 1 to t plus 1 such that n is the sum of bi times the exponential of ai n. And this is technically to be done in space of the endomorphisms of the L submodule of the universal enveloping algebra of L generated by our X. So in particular, we have write a new line. In particular, the adjoint of x alpha over x is the sum for bi times the exponential of the adjoint ai on, I believe this is supposed to be times x alpha on x, which is the sum of the bi on x. Since the adjoint of x alpha is nilpotent, we get that the sum of the bi is 0 and the bracket of x alpha with x is 0. As the x alpha generate L, x centralizes L, and x is in, I'm not even writing it consistently here, as required. Okay, so we remark that the trackpad's grinding on the surface of my table here. Universal Casimir element, which we call a CL, belongs to this funny thing. And this is by our previous calculation, just omitting the representation that we used for it. Now our next topic is how this thing is going to act on our z lambda from before. So v plus is a maximal vector of z of lambda and z belongs to this thing. Notice that h of z of v plus is z of h of v plus is lambda h z of v plus, while x alpha on z on v plus is z on x alpha on v plus is 0 for x alpha in the appropriate weight space, with alpha being positive. Thus, z on v plus is a scalar multiple of v plus. Say chi lambda of z on v plus. The resulting function of chi lambda from this to f is an F-algebra homomorphism called the character, as you can imagine, determined by our lambda. We see that the set of vectors in z lambda on which our z in fancy thing acts as scalar multiplication by our character function is stable under the universal enveloping algebra of L and includes our v plus, hence is all of z lambda. Thus, the action of z in our fancy thing on a submodule of z of lambda is scalar multiplication by our character. Scalar multiplication by chi lambda of z. So Turns out that characters aren't quite necessarily unique based on the lambda that generates them. So we define lambda and mu in H star to be as linked, or lambda is congruent, I guess you'd call this, to mu, if lambda plus delta and mu plus delta are Weyl conjugate for delta being the half sum of positive roots, which we've seen before. And this is, of course, going to be an equivalence relation. And here we're only using it on the integral linear functions. Now it says we're going to choose, I don't know if this is set up for the proposition because it doesn't look like overall it's being super used in it, but choose x alpha in the root space of a positive root. With y alpha in the negative root space, such that the bracket of x alpha and y alpha is h alpha. And then we get a proposition on a new page. I'll let lambda be an integral weight and alpha be from our base. If the integer m as the angle bracket of lambda and alpha is non-negative, then the coset of y alpha to the m plus 1 in z lambda is a maximal vector of weight lambda minus m plus 1 times alpha. The proof is from the lemmas of our previous formula, noting that h alpha minus the action of the angle bracket of lambda and alpha on 1 is within our I that we generated before that. Can't even remember what those are called. But yeah. Ideal. The ideal we generated before. Let lambda be an integral whatever weight thing. Alpha be in our base. Mu be gamma alpha of lambda plus delta minus delta. Then the character of lambda is equal to the character of delta, of mu, sorry. Proof. Since sigma alpha permutes the positive roots, the non-alpha positive roots, and sigma alpha of alpha is negative alpha, sigma alpha delta minus delta is negative alpha. And thus mu is sigma alpha of lambda plus delta minus delta, which is sigma alpha of lambda minus alpha, which is lambda minus 1 more than the angle bracket of lambda on alpha. And by assumption, keep in mind that we have the angle bracket of lambda and alpha being in the integers. If this is non-negative, by our proposition, previous proposition, Z lambda contains a homomorphic image of Z mu. Which would give that chi lambda is chi mu. If, on the other hand, our angle bracket of lambda and alpha is negative, then the angle bracket of our mu on alpha is, keep in mind, the lambda and alpha minus 2 lambda on alpha plus 1 is minus lambda and alpha, which is negative, so this is going to be positive, minus 2 is non-negative, so we proceed on mu unless the angle bracket of lambda and alpha is minus 1, in which case we are done by mu being equal to lambda. Thus, once again, chi lambda is chi mu. From this corollary, we see two integral linear functions linked, I'm not going to write this out, two integral functions linked by a simple reflection have the same character. Because our linkage is transitive, and because our Weyl group is generated by simple reflections, we can give ourselves another corollary. Actually, let's write this all out. Linked by a simple reflection share a character, because this is going to be the pre-work for our next proposition. As our linkage is transitive and the Weyl group is generated by simple reflections, we get the following corollary, which is let lambda and mu be simple and whatever, you know, I forget what the big string of words is. If lambda is linked to mu, then chi of lambda is chi of mu, so they share a character. Now, this is like part of Harsh-Chandra's theorem, and the rest is a lot harder, which is pretty cool because that's what we are doing next. Although, I'm thinking it's gonna be pretty long here because, yeah, our last video we went like, what, 20 minutes overtime, so I think we will end this video here. We might do the Chandra next time. And then there's stuff we'll have to do next time, so I kind of don't like having my videos be super lopsided like this, but it's kind of, the pace is kind of determined by the book, so that's just how things worked out today. Sorry about that.